So welcome back. So you now know that fluctuations exist and that they are in fact an inherent property of all biochemical reaction networks due to the fact that reactions in networks occur asynchronously. That means that whenever there is a synthesis reaction, there can be no simultaneous degradation reaction. So concentrations will fluctuate. Even when a system is on steady state, it means it will on average be in steady state, but around it there will be fluctuations. So if you would do a simple simulation of a system that has the tendency to go back to steady state, so Vs is inhibited by X and Vd is activated by X, such that the eigenvalue, which is their difference, if that is negative, the eigenvalue then the system is stable. So that means that if you would do an ordinary differential equation computation, then it will go back from this initial steady state, it will go back to the steady state. If you would do a stochastic simulation, it fluctuates around it. And if you do another one, you get another color, then what you will see that the other simulation will also fluctuate around the ordinary differential equation description. Okay. So the stochastic description and the ordinary differential equations, they differ. The average dynamics averaged over the stochastic dynamics. So you take an average over all these stochastic curves. Okay, that is the ODE description. Okay, so let's take another scenario. Clearly, if you have this scenario, where the fluctuations are really large, you might wonder whether the average is still a good approximation of what systems do. Okay? Because this could be the behavior of cell 1, and this could be the behavior of cell 2. So cell 1 and 2 are in fact very different. Okay? And to see that, we can take an example that Farrell at some point introduced. So Jim Farrell, in a science paper, something about oocytes. If you look up in the links, so he said that looking at the mean might actually be fooling us, because if I take 6 cells that are genetically identical and the mean value is gray, right? I can also get gray, of course, by having a more gradual measure, right? So here it's really discrete, but here the grayness is gradual. Here averaging makes sense, and here averaging doesn't make sense. We should actually identify two subpopulations of cells, that and that. Okay, so looking at the average behavior of all the cells is not always satisfactory. Sometimes we have to look at individual cells. So what we tend to do in cell biology, so the old-fashioned way, if I have a set of genetically identical cells, so I have an ensemble, so a set of isogenic cells, then the old school molecular biologist would average. So what would this person do if he would look at proteins? And all these individual cells have different numbers of these proteins. Then the molecular biologist would take all these cells all 8 of them, put them in the grinder. Okay, then you get all the cell material out and the molecules. Measure that and get the average, okay? And let's see how much molecules do we have in total. So 5, 9, 11, 14, 15, 19, 24 divided by 7, so we have 24 molecules. 7 cells, right? So that is, we have about, let's say 4, that's 3, about 3.5 molecules per cell, right? So that's what the average molecular biologist would do. But Farrell said, look, you can have this average also in another way. You can have, if you have 8 cells, half of them have 8 molecules. And then clearly the mean is 4. Okay? But this is not, and this is of course, here you're hiding a biological phenomena. You sort of have a differentiated cell population, an ensemble of cells that is composed of 2 subpopulations, whereas here you don't have that. So the idea is now the variance here will be large, and here the variance will be small. Okay? So that's why this measure, so this fluctuation measure, this noise measure, this is exactly what we're going to need. Okay, so in order to quantify now the size of fluctuations, we already know we have to look at its variance. Right? At the variance of the concentrations. So what do? You look at all these individual cells, you look at what their concentrations are, you compute variance. And you have to compare that to the mean. Okay, that's what is 4 molecules per cell. Now, what you have to realize now is that a variance, so if you would make a histogram of all the molecules, right, and the mean number of molecules is here, and the standard deviation is given by the width, which is the square root of the variance in concentration of X. So the square root, so the variance and the mean have the same unit. Right? They're both unit concentration. So that means that the relative width, so relative width of distribution is captured by the standard deviation divided by the mean. So in fact, the relative width is also captured by the variance divided by the mean squared. Okay? And it's this measure that we're going to use to identify whether an ordinary differential equation is a proper description or not. We're going to use this measure, and this measure is called the noise. And it's a significance measure for fluctuations. Okay? So the question that we're going to answer in this lecture is, when are fluctuations significant? And rephrase that and say, when are ODE descriptions satisfactory? Okay, so when are they sufficient? Well, that's when these values are low. Okay, that's what we're going to get at. All right. So again, the behavior of an ordinary differential equation captures the behavior of the mean cell. So that if we look at the behavior of this guy, that guy, that guy, that guy, that guy, that guy, that guy as function of time, that you would get stochastic trajectories. And if all these cells are very similar, then indeed the mean behavior is determined by the differential equation, and the deviations from this differential equation are in fact quite small. So this measure would be small. So for instance, if we would identify in this curve the mean fluctuation size, then that would be very comparable to the mean. So all these cells are in fact, they fluctuate, but they're all in fact the same, apart from these small fluctuations. So you might as well look at the mean. That's when the ordinary differential equation applies. But if you have a huge standard deviation around this mean, of course, then you can wonder whether the ordinary differential equation is really the nice thing to study, the right thing to study. And in the limit, you really have systems, so average cells, whereas a certain value for an average cell property that is determined by cells that vary gradually with respect to each other, but the same mean can be obtained if you have discrete differences between cells. Okay, so you always have to look whether individual cells vary or not, and if they vary a lot, if this is high. Okay, so why is this now so important? So why is it, so what can happen if fluctuations are large? Well, then you may get a phenomenon that you don't get in your ordinary differential equation. So your ordinary differential equations can give you the wrong prediction. So let me give you an example. And that's in fact also one of the computational file examples on Canvas. So if I have a system that's bistable, so we have again the system that we've looked at before. Three steady states, the middle one is unstable. And we already concluded that this one is stable, because if you start at values around it, it will move there. You will never go to the unstable state, because if you start upwards, you go to that steady state. If you start below it, you go to the lower steady state. So if you now add a time axis, and this is the unstable steady state, this is the stable steady state 1, and this is the stable steady state 2, then your ordinary differential description would always do you this, right? If you start here, you end up in the steady state, and nothing changes. But now if you do a stochastic simulation, then something can happen that is ruled out by the particle, by the ordinary differential equation. So you can have trajectories that go like this. That is still fine. They approximate on average the stochastic differential, the ordinary differential equation, but you can also have this, you can jump. Okay, and that's ruled out by the ordinary differential equation description. So that means that in the red case, in fact, so the variance divided by the steady state concentration of steady state 1, okay, so this variance measure is large. So the fluctuations here are really significant, so significant that the fluctuation size can cause the system to pass this border. And now the system jumps from one basin of attraction to the other one, or back. Okay, and that's not described by the ordinary differential equation, that's impossible. It will never give this outcome. So this tells you that these ordinary differential equations are limited when fluctuation sizes are large, because then you can have these spontaneous jumps between different basins of attraction in bistable states, in bistable systems. So that's when you have to think about a stochastic model rather than an ordinary differential equation. Okay, so that means, so we require now a method to determine delta x. Okay, so this noise measure, we want to determine that. You can do that by simulations. You can also do that analytically. Analytically, this can be done with the linear noise approximation. Now it has some, of course, it has some limitations because it's an approximation, but for the purposes of today it suffices. Now I'm not going to explain linear noise approximation, you'll find the references in the syllabus, it's beyond this course. It's actually a very fun, I really enjoyed working on it myself, I still use it very often, so it's a very useful method. But here we're just going to look at one of its outcomes. So let's look now at a system that has a single steady state and it's stable. So the eigenvalue, which is the difference between these two, is in fact negative. So we have a stable steady state. And we want to know now what is the equation for this. Okay, that's going to be minus 1 over squared, 1 over the volume, and the steady state flux divided by the eigenvalue. We check whether that's correct. Yeah, that's correct. Okay, so what do we find here? Okay, so we are looking at the noise. So this is the mean concentration, so the steady state concentration. So this is the volume of the system in which our reaction occurs. This is the steady state flux, so the rate at steady state at which molecules are converted. And this is the eigenvalue. We've already determined it to be negative, so it's negative. So that guy is positive, that guy is positive, that guy is positive, it's negative, so we have a negative sign to make it positive. Alright, so this tells us how large the fluctuations are relative to the mean behavior in this system. And we see now that there are several ways to make it small. There are trivial ways. Of course, if this is small, then this is going to be large. Yeah, that is sort of obvious. That's not what we're interested in. And the most important effect is that this thing is large, right, when volume is small and lambda is small. Okay, those are the two things we have to understand. When is this going to happen? Okay. So let me start with lambda is small. Okay. So is large when lambda is small, or 0 even, right? Okay, when does that happen? That happens when the system becomes unstable. This happens when system becomes unstable. So, when bistability arises or this appears, or when oscillations arise or disappear. Okay? So that is, I think disappear is what one is. But, okay, that is when the eigenvalue is small, and that's when this is large. So later we're going to look at oscillatory systems and bistable systems, and exactly when they become bistable or when they become oscillatory, this is large. So that's when the population of cells are very dissimilar. Okay, so then a very heterogeneous population of cells in the ensemble. So the average doesn't really predict what an individual cell does. Okay, so that's one way to get to get a condition where the ordinary differential equation doesn't apply. Now the second condition is when v is small, right? So let me explain why that is. So the question is, why is large when volume is small? Okay, so when we change the volume in this equation, okay, so this is the equation we're looking at. So when we change the volume here, we keep the mean fixed. So the mean concentration, right, that is of course the mean number of molecules that you have divided by the volume. So when you change the volume, but you keep the mean concentration fixed, you have to change the mean number of molecules. So if you halve the volume, you will have to halve the number of molecules. But minimal fluctuation size is one molecule. You cannot have half a molecule. So when you start decreasing the volume, the number of molecules in the system changes too, and their number is going to get closer to the minimal fluctuation size. So by definition, fluctuations become more significant. When nx, so the mean number of molecules, goes down. Because the minimal fluctuation size remains 1. So fluctuations become more and more significant with respect to the mean number of molecules, because their size, the minimal size, remains 1. So fluctuations become more and more significant. Okay, so that's why this guy increases with small volumes and small eigenvalues. When the system becomes unstable, it becomes big. That's when individual cells in your sample will greatly vary and when the volume is small. Okay. Now we understand when fluctuations are significant. You should look at this measure. This is the outcome of the ODE, and this tells you how large deviations are from the outcome of the ODE. If that therefore is large, then you should use a stochastic description. We can approximate these values using linear approximation, and then for this case we'll find a fairly simple equation that has the mean concentration in it, the volume, the flux, the eigenvalue. This guy is large, then the ODE doesn't work properly, at least it's not reflective of individual cell behavior. When is that? When V is small or the eigenvalue is small. Alright, that's it for now. Thank you very much.